we're going to do this lesson 4 first, and then we're going to come back to lesson 3. That's why it says lesson 4. And the reason why I wanted to do it this way is because we just talked about yesterday how limits typically equal function values. Example, if I asked you the limit as x approaches 3 of x squared, the answer is 9. You don't have to plug in 2.99999 and 3.00001 and square those values to see that you're going to get values close to 9, because I know I have a point there at 3,9. And I know that we'd be approaching that 0.39 because x squared is nice and smooth and what we call continuous. Here's the 0.39. I'm approaching 9 from the left and the right, and I have the 0.39. Okay? And this is a typical situation for continuous functions. We will now have a calculus definition of what it means to be continuous. A continuous function is continuous when limits equal function values at specific x locations. Here, we're talking about C being the x location. Okay, now what is a function not continuous? Well, if this means we're continuous, what would make this not be true? Well, if there's no limit, if there is a limit but no function value, or if there's a limit and a function value but they don't equal each other. And instead of no function value, say no fx. Now, for most of the examples we're going to start with, we're going to be looking at expressions like this. Okay? And if I give you an equation like this, what you will find is that the discontinuities will be locations where there isn't a function value. And when there's not a function value is usually a situation when you have a denominator equal to 0. You are not allowed to divide by 0. So if you are looking at some sort of expression, some sort of function, and all of a sudden you have a 0 in the denominator, this means you don't have a function value. So for most of the first kind of sets of examples, we're going to focus on that. We're not going to have a function value when we have a 0 in the denominator. Okay? But we'll come back to that because let's visually be able to see the situations we might have. Okay? Here's the different types of discontinuities that we will need to be able to identify given a function. First, a hole. Here we have a limit but no function value. We call this a removable discontinuity. And in a function, if I plug in a C value and I get 0 over 0, that's typically an indication that we have a hole. A jump. Maybe there's a function value, maybe there's not. Well, the limit doesn't exist, okay? So that's why the limit doesn't equal the function value, because the limit does not exist. And we typically see jumps with piecewise functions. But there's another type of function where we will see a jump that we'll look at later. A vertical asymptote. When we don't have a function value, but our function will be approaching that and either trending up towards positive infinity or like down towards negative infinity. We will look more into asymptotes and vertical asymptotes next class. Okay? Now, what I'll tell you right now is that you will see a vertical asymptote, and I'll tell you why next class, when plugging in a value, you get some number divided by 0. We'll discuss more why number over 0 means vertical asymptote next class. Okay, but if I plug in a value and I get a number over 0, that's a vertical asymptote. Now, these are called non-removable. Okay, and it's either a non-removable jump or a non-removable vertical asymptote. Instead of saying this is a non-removable vertical asymptote, we'll either do VA for short, or we need to be comfortable calling it an infinite discontinuity, a non-removable infinite discontinuity. Okay, now, reason why this is removable is because if I just had a point, man, I could just like fill in this dot and all of a sudden I have a function value that would be equal to the limit that I already have. Okay, so this removable discontinuity has a location. As we go through and evaluate functions and their continuity, if we ever find that a function has a removable discontinuity, we will be asked to find the location of the removable discontinuity. Well, remember, that's just like finding the limit. As x approaches this c value of f of x, and L stands for that location. Okay, so just to remember, and just to put this in kind of like big bold letters, how do we know if we have removable or non-removable discontinuity? If you see 0 over 0, you are thinking removable, whole. If you see a number over 0 for a certain x value, you're thinking non-removable, infinite, or vertical asymptote. There's another situation of like jumps. Jumps are typically piecewise functions. But there's another type of function that we'll see is a jump. I'm going to spread these up a little better. Okay, good. So remember that. All right. I got different situations that we're going to get into before we get into this. Okay? Finding the locations of removable discontinuities, finding limits without the use of a calculator. Okay? Now, what we will be doing frequently is we will be factoring functions so that we can see when a denominator equals 0. Now recall factoring. We are looking for two numbers that go into these binomials, where I know that we have x and x as the first term of my binomial. X times x gives us x squared. Well, I need to pick two numbers so that when I multiply the two numbers, when I do the distribution process, The two numbers multiplied together give me this negative 15. So I put a dot over the negative 15 because I'm thinking, okay, this number times this number has to equal negative 15. And I'm also thinking, okay, well, this x is going to be multiplied by this number, and then this x is going to be multiplied by this number when I distribute everything, and I'm going to add those two x quantities together. So that's why I'm looking for the same two numbers that add to get negative 2 and multiply to get negative 15. A lot of people have done this in the past. I don't know what this is telling you, but if you're comfortable using this, go ahead and use that. I like to just use a dot and a plus and say, okay, these two numbers, negative 5 and 3, when I multiply them, they get negative 15. And then through the distribution process, gives me negative 5x plus 3x added together gives me negative 2x. Okay, so that's what I do. Okay, so I factored. Why did I factor? Because I want to figure out when denominators equal to 0. And immediately I can say I have a discontinuity at 5 and negative 3. It's a discontinuity because the denominator equals 0. Okay, so that's one thing I'm going to do. I'm going to find the locations of discontinuities. The next thing I'm going to analyze is this a removable or a non-removable discontinuity at these locations? So what type of discontinuity do I have? Well, if I plugged in 5, I would get 8 over 0. I know I would get 0 because plugging in 5 would be 0 times 8, that's 0. So again, I have some number over 0. That is telling me that I have a vertical asymptote or a non-removable discontinuity. Non-removable infinite discontinuity. If I plugged in negative 3, now we don't have to do this in the future because I'll show you how we know you're going to get 0 over 0. But if I plugged in negative 3, I would get 0 over 0. That is telling me that I have a removable whole. So I would say that 5, non-removable, put like an R above it. 3, removable, put an R above it. But I'm asking you now to find the location of the removable discontinuity. So if I looked at the graph of this, I don't know what it looks like. I know that at negative 3, I have a hole. At 5, I'd have an asymptote. I want to figure out where is this hole's location. Is it, hold on. Is the hole going to be up here? Is the hole going to be down there? How am I going to find that? Well, if you had your calculator, and I'm just going to show you with the calculator. If you had your calculator, and this was last class, you would know what to do. Please discuss with your neighbors, confirming that you know what you're doing when I ask you to find where is this hole located. Go, discuss. Okay, ready? As of last class, what you should have been telling your neighbors, because you cannot type in -3 and get a function value, it's blank. There's no function value defined. You told your neighbors, hopefully, that you should be typing in -3.00001. And you get -0.125. You should be typing in -2.99999. And you see, it's looking like I'm approaching a y coordinate of -0.125. It's like 1/8, I think. Okay, so that's how you would find it with a calculator. We're not going to be able to use our calculator for the rest of this unit. We need an alternate approach. Watch what we can do. Okay? I can notice that, oh, I got x plus 3 here, x plus 3 down there. Can't I just cancel those? I can. But when I do that, I have manipulated my original function. I'll show you in a second. And I'm creating what I'm going to call f star, which is now just 1 over x minus 5. Now in f of x, I can't plug in -3. I get 0 over 0, undefined. Okay, so f of x can't plug in -3. -3 is a discontinuity. But in f star of x, I can plug in -3. And if I plug in -3, I get -1/8. The same value that I saw, -1/8, using my calculator. What is very interesting about this process is if I graph 1 over x minus 5, and you're going to see it in a different color in red, and I'm going to make sure you can see it. Let me try to change this to like a dot. Maybe red dot will show up. Let's try. It ends up going exactly over my original function. Looks like it's the exact same thing. However, it's got one difference, and you can see it in the table. At -3, where my original function says, nope, we have a discontinuity, we have a hole, our new function fills in the hole so we can find the location of that hole. So this is how we're going to find, now, locations of holes without using a calculator. We will algebraically manipulate things. So what I'm going to ask you to do is first note that this is non-removable. This is infinite. Note that this is removable. And then tell me that the location is there. And turns out what you've just done is answered this problem. What is the limit as x approaches -3 of x plus 3 over x squared minus 2x minus 15? You algebraically simplified something, created a new function, then you plugged it in, and that's how you'll be able to answer that that's -1/8 in the future without using your calculator. Okay, so calculators are gone. I want you to understand the concept of getting very, very close to something, because we're going to be using that in the future. But right now, our calculator will not help us anymore. Okay, so that's how you find locations of removable discontinuities, and that's what we're going to be doing a lot of here. Finding the discontinuity locations, if it's removable, finding what x values we have discontinuities, figuring out if they're removable or not removable. If they are removable, find the location. Okay? Some things we need to remember. Factoring difference of squares. Remember, a squared minus b squared factors to a plus b times a minus b. X squared minus 1 factors to x plus 1, x minus 1. Where do I have discontinuities? You're first going to be looking at when our denominator equals 0. I know at -1 and at 1, if I plugged both of those values in, I would get 0 in my denominator. Now, I don't have to go through the process of plugging in -1 and plugging in 1, because I can see, okay, this cancels. So yes, since that's removed, this is the location of my removable discontinuity, x equals 1. I would get 0 over 0 if I plugged 1 into the original function. Now, after canceling, I have created, just really quickly, this f star, I can plug 1 into the simplified 1 over x plus 1, and I get the location is at 1, 1/2. I can confirm that using my calculator. If you're doing your homework and you're like not sure what you're doing, go ahead and graph. Plug in 0.9999. Plug in 1.0001. Now, this is confirmed that -1 is non-removable, because in my original function, I can't plug in -1. In my simplified kind of f star function, I can't plug in -1 because I'd get a number divided by 0. So this is non-removable, and it is an infinite discontinuity. Again, for all of these expressions like these that we're going to look at, non-removable will mean infinite. The other type of non-removable is a jump. Jumps occur with piecewise functions and another type of function we're going to see. All right, you guys please do the one on the right. Find the locations of discontinuities. Remember, you can factor out a greatest common factor. So I would factor the denominator so that I can set it equal to 0 and solve easily. But you guys do the rest. Please check your answers with a neighbor. Okay, go ahead and check.
I thought we were doing this one. I got you.
Okay, well, doesn't matter. We're good. Good start on that one. Okay, when does your denominator equal 0? Before simplify.
Okay.
Yep.
And this is where your hole's at.
Yes. But what's that coordinate? X equals -1 will make this 0.
Okay.
0
Okay.
will make this 0. So our two numbers are x equals 0 and -1.
Okay.
0 is where our hole is because I can cancel that.
Yeah.
-1 is where my asymptote is.
Okay.
What is the location of the hole? Yep, you got it. Okay, so factoring allows me to easily see visually when my denominator equals 0. My denominator will equal 0 at 0 and at -1. I can see here if I plugged in 0, I'd get 0 over 0. I can also see that I can remove those x's, which is kind of also telling me that that's my removable discontinuity. Now that creates my kind of simplified f star function, 1 over x plus 1, which I can plug 0 into, and I get 1 over 1, which is 1. So the removable's location is at 0, 1. Now I can see I can't plug in -1 here. I'd get a number over 0 if I plugged it into any of these f's or f stars. That is confirming that this is my non-removable infinite discontinuity. It's my vertical asymptote. Okay? Please do this one here. we know an x squared plus an x plus a number can be factored to be x plus something times x plus something else. Whether it's positive or negative values. Those two numbers need to add to get you your middle and multiply to get your negative 6. Careful. Please check with your neighbors. Okay, now. Hold on. It is positive 3. Yep. Great. What are the two numbers that add to get -1 and multiply to get -6? Good. Good. What's the location? Plug in 3. Okay, so I can factor the denominator to be x minus 3 times x plus 2. There are two ways I know, well, I first know that when the denominator equals 0, that's when I'm going to have a discontinuity. So the denominator is equal to 0 at 3 and at -2. Okay. Two ways to figure out that x equals 3 is my removable discontinuity. If I plugged in 3, I get 0 over 0. Or I can see that I'm removing kind of that stuff. I don't like to say that's like very mathematical or technical, but you can kind of see. Now, I create f star, which is the simplified f, which removes the location of the hole. I can plug 3 into this and see that I get the location 3, 1/5. You could confirm that using your calculator when you're doing the homework. Now, if I plugged in -2 into the original function, into the simplified function, I would still get a number divided by 0. A number divided by 0 is telling me I have a non-removable infinite discontinuity. Okay, let's do the next one. Now, the next one, we got a couple steps in the factoring of our denominator. My first step would be to factor out the greatest common factor. 2x can be divided out of 2x cubed and 18x. So if I divide 2x out of 2x cubed, I have x squared. If I divide 2x out of -18x, I have -9. And yes, my numerator is x plus 4 and x plus 3, because I'm an expert trinomial factor person. I can go further, though, with the x squared minus 9, because that's an a squared minus a b squared. I got x plus 4, x plus 3 in the numerator, denominator 2x. This is x plus 3, x minus 3. Now, that I've done that, we need to be comfortable saying when our denominator equals 0. Please tell your neighbor, when does the denominator equal 0 for which x values? What some people forget is that 0 also cannot be plugged in, because 2 times 0 is 0, 0 times anything is 0. So don't forget about this 0, because I factored out an x. Now, if I just factored out a number 2, if this is just 2, well, then 0 would not be a solution. But I did not just factor out 2, I factored out 2x. Okay, so 0 is one of our discontinuities. Now, we can visually see, as well as we could check by plugging it in, -3 gets removed. I still can't plug in 0, I'd get a number over 0. I still can't plug in 3, I'd get a number over 0. So both of these are non-removable. They are infinites. I'm not even going to write infinite anymore. I need to find the location of my removable discontinuity. Well, after simplifying, I've created this f star. I could plug in -3. So f star of -3 is 1 over 2 times -3 is -6. -3 minus 3, -6, positive 36. So this removable discontinuity has a location of -3, comma 1 over 36. Okay, let's go to the next page. Okay. Please do this one. Start by factoring out a greatest common factor. I can divide each of those terms in the denominator by 3x. I could pull 3x out of all of those terms in the denominator. Please pull 3x out of all those terms in the denominator. After you've done that, maybe you could factor what's left over after pulling out the 3x. Then you can see visually which x coordinates will make that denominator 0. And then from there, we can talk about removable, non-removable. If they're removable, what's the location? trying to be so neat. I just fail. Negative 5 times 4 is negative 20 times 3 is negative 60. So at 0, I have a removable. The location is 0, comma, negative 1/60th. Both 5 and negative 4 I can't plug in from the get-go because it'd give me a number divided by 0. So I know for certain that both of these are non-removable. Infinite discontinuities. Okay, I'm going to do the next 3 for you because they're kind of tricks. Okay. This bottom one, right one. You can't factor this. If you set it equal to 0 and tried to solve, you get x squared equals negative 2. X would equal plus or minus root negative 2. We do not have to worry about imaginary numbers in this class. So we would say that the denominator never equals 0, or that there are no solutions for this. Thankfully, in this class, you don't worry about imaginaries. Since there's no solutions, and the denominator is never equal to 0, what would we say about the function? Discuss with your neighbor. Since there are no points when the denominator equals 0, what would I say about x plus 2 over x squared plus 2? Discuss. Mr. Dunlap, what do you think?
That it's a continuous function.
It's continuous. It's continuous everywhere. There's no discontinuities. There's no solutions, so there's no discontinuities, which means we are continuous everywhere. Okay? This guy, I think I tried to set up the function so that stuff would cancel, but it didn't work out. Watch what happens. This is x squared squared. This is 2 squared. Okay? So this is a difference of squares. I could write it as x squared plus 2 and x squared minus 2. We just talked about how x squared plus 2 never equals 0. But x squared minus 2 does. Now you can either factor this or solve to get x equals plus or minus root 2. So I do have 2 discontinuities at positive root 2 and at negative root 2. Sometimes we're like, oh, this can't factor, but actually you could factor the x squared minus 2. It can factor to be x plus root 2, x minus root 2. All right. Now, notice, none of these cancel with x minus 2. I plug in root 2, I plug in negative root 2, I'd get a number divided by 0 no matter what. Both of these are non-removable. Since they're both non-removable, I do not have to worry about f star or locations of anything. This guy. You need to be comfortable factoring a trinomial, quadratic, x squared, but with the leading coefficient not 1. Now, there are a lot of techniques that you might have learned over the years to factor that. If you remember those techniques, great. I will tell you that typically in this class, it will be easy enough for you to guess and check to factor this. You got to understand how you distribute to be able to kind of guess and check and do this process. My leading term is 2x squared. The only way I can multiply two things to get 2x squared is for my leading terms to be 2x and x. Okay? Now my last term is -6. I got two options, -6 and 1, or 1 and -6. That's one option. The other option is 3 and 2. -3, +2, +3. We got to figure that out. This is where you got to look at the other term. 2x times this number plus x times this number need to add together to get -1. Now, I'm thinking -3 plus 2 is 1, right? Well, if also -4 minus 3 is -1, right? That's why I'm thinking if this is -2 here, 2x times -2, that's -4x. And if this is +3 right there, 3 times x, 3x, 2x times -2, -4x, add them together, I get -1x. Now, if you don't understand how I got that, or if that doesn't work out for you, well then, talk to me before or after school. I'll give you a different technique to use, okay? Now let me just double check. 2x squared minus 4x plus 3x. Okay, good. Now go ahead and change this problem so this is x minus 2, just for fun. Now there's two locations where this will equal 0, and when x minus 2 equals 0. I don't have to show this all the time, but just to show you, like, when does this piece equal 0? Subtract 3 divided by 2, you get x equals -3/2, and x equals 2 are the my locations of discontinuities. I can see that if this is x minus 2, that x equals 2 is removable. The location, well, if this is f star, I would plug in 2 into this special one, and I'd end up with 1/7. The -3/2, I won't be able to plug into the top or the bottom. I will be able to plug into the top and always get a number, regardless. The bottom, it'll get 0. This is why this is non-removable. Okay, so we need to be prepared to factor simple quadratics where a is not 1. If we don't remember how to do that, or if you need practice, I'll give you some. But there's usually 1 or 2 that show up on an entire AP test. Whereas factoring is factoring regular quadratics with greatest common factors and all the other stuff that we've done, very, very important, actually. Sine of x minus 1/2. Well, I'm going to have to figure out when this is 0. There's no factoring involved here. It's just when. Sine of x equals 1/2. Add 1/2 to both sides. Look at that. It's a trig equation. We can solve this. When is sine positive 1/2? I'm thinking about a vertical being up and positive 1/2. That is going to be my short 30, 60, 90 triangle at pi/6 and at 5 pi/6. Now what's interesting, and I actually don't know the answer to this, is that if I plugged in pi/6, I would get 0/0. So I think I have a removable hole. In 5 pi/6, I would not get 0/0, so this would be non-removable. For this situation, let's just not stress out now. I'll tell you in the future how you'd find the location of this removable hole. But for right now, let's just go with pi/6 is removable, 5 pi/6 is not removable. Since you don't know what to do, what to factor, it's not a problem for right now. It'll be a problem for the future. Okay? So it won't be on a quiz or anything. Don't worry. Tan x. Well, sine x over cosine is tan x. Need to figure out when tan is ever having a 0 in a denominator. So that's when is cosine equal to 0. Think about it. My adjacent side needs to be 0. So cosine of 0 is 1. Pi over 2, the adjacent side is 0. 3 pi over 2, the adjacent side is 0. These would both be non-removable. All right. Going back to the beginning, we talked about jumps and how jumps are usually piecewise functions. We've introduced this function last class. I'm reintroducing it to you again. This is the other type of function that has a jump that is not a piecewise function. We might think, oh, x equals 0, and since I get 0 over 0, it's removable, but that's not the case. X equals 0 for this type of absolute valued function is a non-removable jump. Here, we might think, oh, 3 over 3. I mean, if I plugged in 3, I'd get 0 over 0. That would mean it's removable. No, x equals 3 is a non-removable jump. And here's why. If you're talking about x's bigger than 0, the absolute value would keep the top positive, and the bottom would stay positive. X divided by x is 1. So, if I'm looking at the graph, if I'm to the right of 0, I'm up here at 1. If x is less than 0, well, that's a negative value. The absolute value would make it a positive, so I'd still have a positive x. The denominator would be a negative value, so this would turn into a negative x. Well, simplify that, that's negative 1. So we'd have values that are only negative 1. We have a jump, not a hole. The same goes here, but we would focus on 3. If I plugged in values bigger than 3, I'd have a positive value divided by a positive value, that's 1. Less than 3, I'd have a positive value divided by a negative value. It would be negative 1. This type of function you need to be familiar with. You will see one-sided limit questions, like over here they'd ask what's the limit as x approaches 0 from the left of this. You need to be comfortable saying, oh, that's negative 1. Or if I ask you, what is this? You need to be comfortable understanding and saying that that's 1. And we need to also be comfortable saying that we have a non-removable jump. Okay? So let's go back at our notes and say we got either piecewise functions for jumps or this kind of absolute value of something divided by the same thing function. Okay. When do you have a non-removable jump? Either a piecewise function or an absolute value of x over x, something like that. Cool. Well, let's talk more about piecewise functions. For most of our piecewise functions, each individual piece, if you analyze them separately, like x squared or 2 minus x, if you just look at them separately, they are continuous. Okay, if I just looked at x squared, it doesn't have a denominator. When you don't have a denominator for you guys, you just have to worry about, okay, I can plug in any x. There's no denominator. It'll never equal 0. So, no denominator, continuous. No denominator, continuous. But we're not going to use both of them at the same time. We're going to use this one when x is less than or equal to 1. We'll use this one when x is greater than 1. So I have a situation where I'm going to use x squared up until 1, 1. 2 minus x starts at x equals 1. Well, if it starts at a different location from where x squared ended, it's a jump. If it starts at the same location, we're continuous. Which means when we deal with piecewise functions, all we need to worry about is this coordinate. And does my top piece meet up with my bottom piece at that coordinate where I leave one and pick up the other? How I like to kind of show that is I'll call this f sub 1 and this f sub 2, and I will check. Do they meet up with each other at 1? Does 1 squared equal 2 minus 1? Yes, this function's continuous everywhere. No jumps. If I have 3 pieces, well, let's label them f sub 1, f sub 2, f sub 3. F sub 1 may or may not meet up with f sub 2 at 1. So we got to check. Do they meet up? F sub 2 may or may not meet up with f sub 3 at 2. Now, it's important to remember these are x values. Plug them in for x. Right now, it's kind of obvious, but in the future, it is important to remind each other. This piece needs to meet up with this piece at 1. 4 equals 9. Nope. We have a jump discontinuity at x equals 1. Non-removable jump. This is a piecewise function. They jump. It's not a denominator equal to 0. Here, 10 minus 2 equals 6 times 2 minus 2 squared. 8 equals 12 minus 4. 8 equals 8. We're good. We're continuous at 2. We're continuous except for x equals 1. I don't want to spend time on this. Move on. These guys. This really isn't a piecewise function. This is a pointwise function. Why is it not a piecewise? Because I'm using this top piece for every single x value except for just 2 points. Okay? So, if you think about it, and let's just think about it. I'm not going to be accurate, but I'm just going to kind of sketch an idea of things. At -3, I'm going to use the point -1/5. Okay, cool. No matter what, at -3, I use the point -1/5. At 2, I'm going to use the point 1/4. Okay, good. Well, hopefully, this function will end up passing through those 2 points. If it passes through those 2 points, it's continuous. But what we're going to see is that it's not going to happen like that. What we're going to see is that this function will have holes or asymptotes. Now, if I end up having an asymptote, maybe at -3, well, we're not continuous at -3. We have an infinite discontinuity. But maybe I have a hole, and maybe the hole is located right at that point. And if the hole is located right at that point, well, then we are continuous at that location. Okay? So what we have to do is actually analyze this function x plus 3 over x squared plus x minus 6 a little bit more and see, does it trace over those points that I just plot out? All right, well, let's just look at x plus 3 over, let's make this our f star. Let's start simplifying. This is x plus 3x minus 2. Okay. We notice that for f star, for just this piece, x equals 2 is a non-removable infinite discontinuity, which means for the graph of x plus 3 over x squared plus x minus 6, I know this point isn't going to make it continuous because I'm going to have this here and that here, or something like that. So immediately, discontinuous at 2, non-removable. Now let's look at x equals -3. I can see this is removable. Okay? Removes, or I get 0 over 0. And if I plugged in -3 to find the location, I see the location is at -1/5. So that piece has a removable discontinuity, or it has a hole at the location -3, -1/5. Well, it turns out if I graph, and I don't know what it looks like, I'm just like guessing here, I would end up with a hole right where that point -3, -1/5 is located. We actually are continuous at that location. So I would actually say, well, continuous because of the point -3, -1/5 being right here, but we are not continuous at 2. Okay? You guys see if you can do the one on the right. All right. If I just looked at x over x squared plus x, I'd see it would have a non-removable asymptote at -1, a removable hole at 0. The location of the removable hole is at 0, 1. Well, I have a point 0, 1. So now I do have a function value at 0, 1. The hole got replaced by the point. But I would still have a non-removable asymptote at x equals -1. Okay? Fantastic. There are other ways that we can ask questions involving continuity in piecewise functions or pointwise functions. And that's, hey, make sure this function is continuous. So we're going to find the values for A or B or C so that the following piecewise or pointwise equations are continuous. It goes back to seeing there's no denominator. If you don't see a denominator, this piece will be continuous, this piece will be continuous. All we got to worry about is, do they meet up with each other at 5? So, does f sub 1 meet up with f sub 2 at 5? Now, before we go too far, remember, this is an x value. So plug in 5 for x, not for c. I'm trying to find c, and this is f of x. So this is 5 squared minus c equals 4 times 5 plus 2c. 25 minus c equals 20 plus 2c. Solve. All right, please do the second one for me. So you get 6a equals 4. A is equal to 4/6 or 2/3. Anybody else get that? Yeah? Okay, good. All right, so this is a different type of problem. Same idea, though. Make sure the pieces of our piecewise function meet up. Oh, 3 pieces. 2 letters. Okay. Well, just like we did before, make sure first piece meets up with the second piece at -2, or I leave one and pick up another. Make sure the second piece meets up with the third piece at 1. All right, let's set up some equations. So far so good. Do we get negative 20 equals negative 2a plus 2b? It's one equation. Get a plus 2b equals 6. Just by plugging in negative 2 into the first and second, and 1 for x into the second and third. Great. I do now. Well, there's one thing I can do very quickly is simplify this equation by dividing by 2. Like, divide the left and the right by 2. Maybe, like, not worry about things, multiples of things if you don't have to. You'd get the same answer if you didn't do this, though. Okay. Now, this is a system. We have dealt with systems of equations since Algebra 1. 2 equations are needed if you have 2 unknowns. If you're ever trying to solve something with 2 unknowns, and you don't have 2 equations, you won't be able to solve it. We have like 2 lines. We need to find the intersection of both lines. In this class, most commonly used and what you should look to use every single time is substitution. That means solve one of these equations for a variable. Probably the variable that's easiest solved for is a smart idea. And then substitute it into the other equation. So, I don't know, solve for b here. B is equal to negative 10 plus a. Substitute it into your other equation. You could do this numerous ways. Just pick a way and make sure you are careful and neat and orderly and you're getting everything correct. A plus 2 times b. You get a plus negative 20 plus a equals 6. 2a equals 26. A is equal to 26 divided by 2, which is 13. Oh my gosh! I can't believe that. Sometimes when you're talking and you're going slowly, your brain acts slowly. That was my brain acting slowly right there. So 3a is equal to 26. Divide by 3. 26 thirds. Gross. It's okay. We need to be comfortable working with fractions and sometimes getting gross answers. Not everything's going to be in whole numbers in this class. Now, it's great. I already know what a is equal to, what b is equal to. B is equal to negative 10 plus a. So I could take this 26 thirds and just plug it in for a, and I'll find b. You need to be able to write negative 10 using a common denominator, multiply negative 10 over 1 by 3 over 3, you get negative 30 thirds. Negative 30 thirds plus 26 thirds is negative 4 thirds. Okay? Why don't you guys try the next one? Hopefully the numbers will be nice and easy instead of 26 thirds and negative 4 thirds. That was nice. Okay, those are piecewise. Here comes a pointwise. I need to make sure that this entire function is continuous, which means I need to make sure this point at 3 meets up with what this function is approaching. Now, watch. I can't just plug in to x squared minus 4x plus 3. If I plugged in 3, I got 0 over 0. This is the situation where I need to take this and factor to find the locations of possible holes or asymptotes. Whoops. And I'm creating this kind of, if this is G1, this is G1 star. And I can see when x is equal to 3, I have a removable discontinuity, and that location is at 3, 2. So that means that top piece is approaching 2 as x is approaching 3, or the limit as x approaches 3 of this top piece. Doing this by hand is 2. Well, this point at 3 has to equal that number. So it's like I got this piece at 3. I have a hole at 2. I need to make sure this point 2 when x is 3. Do we have another one like that you could practice? Nope. So your homework, you'll have more like that. It's a tricky question. I brought it up here just so you see in the future you're not too tricked out by it. What positive values for a is f of x continuous? The answer is none. Because if you set this equation x squared minus 8 equal to 0, you will always have values for a that'll make the denominator 0. Now you might be thinking, well, what if it's 9, Mr. Messner? If I put 9 here, don't I just cancel that? Well, you do, but that just means they're removable discontinuities at 3 and negative 3. They're discontinuities nonetheless. There is no value that you could plug in for a so that the denominator never equals 0. Unless, actually it's not true. Oh wait, it's positive. I was going to say, like, if a was negative and this is x squared plus a, then we'd be good because x squared plus a never equals 0. Like if I had a negative value in that square root, then I'd say, that doesn't work. But if a is positive, we can always take the square root of positive. All right, finish things finishing things off with a theorem, which you just need to understand the concept of, and I don't want you guys to think that this is tricky, because it's really not, okay? It's called the intermediate value theorem, and it deals with continuous functions. Now, if I read this entire statement out, it might not make sense to you. But if I just showed you this picture, it might. Let's say you have a function. And you know that this function is continuous. Okay, intermediate value theorem is like the continuous theorem that we need to know this year. We only have 2 theorems we really need to know. This is one of them. Okay, we know the function is continuous. And I have 2 points that I know exist on the function. But I don't know how those 2 points are connected. But I know that you connect them in a continuous manner. Well, no matter what y value I choose between these 2 points, let's say I choose this value right there. There's guaranteed to be a point on an x where we will produce that y value, no matter how you connect those 2 points. What I'm saying is, like, if you have 2 points and you know the function's continuous, they have to be connected somehow. Like that. Like this. Like that. Guaranteed to have an x value that produces this y value somewhere. Whether it was like this or like that, and then the x value is right here, okay? And you'll see how we're going to apply this to certain situations, okay? So we are guaranteed to have a y value, any y value between our 2 points, get hit by some x value. I'll write that. Every y value gets hit for at least one x value between your points. Okay? This is how we're going to apply it. We're going to look at some crazy equations that we're trying to solve. Like, here's a function. When does this function equal 5? Okay, so when does this function equal 5? That's the question. Do not try to solve this. You will not be able to. But you will be able to show that there is a solution, and you'll be able to show where that solution is located. You following me? Don't try to solve. Don't solve. You won't be able to. Instead, we're going to show that there is a solution. We'll be able to show exactly where that solution is located. Because I know f of x is continuous. Who can tell me why I know that function is continuous? Because there's no denominator. If you don't have a denominator, you're going to be continuous, unless you're like tangent. Well, tangent does have a denominator. It's sine over cosine. Continuous, no denominator. Okay, great. Well, let's find 2 points. I'm looking at this interval 1 and 2. Well, f of 1, 4 minus 6 plus 3 minus 2. So that's negative 2 plus 1. Negative 2 plus 1 is negative 1. Okay, great. Let's look at 2. So this is 8 times 4 is 32, minus 24, that's 8, plus 6, which is 14, minus 2 is 12. So this is 12. Okay, so I don't know what the solution to this equation is, but I do know I have 2 points. 1, negative 1, and 2, 12. I am guaranteed to hit 5 at least one location somewhere between this point and that point. This shows me that this location exists. What the value is, I don't know, but I do know it's between 1 and 2. So this is our statement. And you're going to write down the statement. Since f of x is continuous, and I know that f of -1 is -1, and f of 2 is 12, and x between 1 and 2, you can either write between 1 and 2, or you can use interval notation, saying x is between 1 and 2, such that you can use st for short, f of x equals 5. By the intermediate value theorem, sorry. By the intermediate value theorem. Okay, the next couple examples, I'm just going to say verbally. Oh, but we want one extra step. We want to explain that the function has a solution, and we want to find the solution. All right, cosine, continuous, fantastic. F of 0, I know is 1. F of pi, I know the cosine of pi is -1. So, since f of x is continuous, and we have the point 0, 1 and pi -1, there must exist some x value between 0 and pi such that f of that x value gives you 0. Now, we want to go a step further in this situation. We want to actually find the solution. In most situations, I'm not going to require you to find the solution, but I actually know that at pi over 2, which is between 0 and pi, cosine is equal to 0. This guy. Is this continuous everywhere? Discuss with your neighbors, please. Is that function continuous everywhere? No, it's not continuous everywhere. It's got a denominator. When x is 1, we have a discontinuity, an asymptote. But is 1 between 5/2 and 4? No. So this function is continuous between 5/2 and 4. All right. Now I'm going to go ahead and use my calculator to quickly find what f of 5/2 is. So 5/2 squared plus 5/2 divided by 5/2 minus 1. 2.5 minus 1 is 1.5. I get 5.8333. That's 35.6. Whatever, I'll just leave it as 5.8333. All right, it's under 6. If f of 4 is over 6, we can use the intermediate value theorem. 1620 divided by 3. That is like 6 2/3. All right, good. Since this function is continuous between 2.5 and 4, I have an x value such that f of x, and that x value is between f of x equals 6. Now they ask you, go ahead and find that value that you guarantee exists. This is part of the directions. It's like, show that the value exists and then find the value. I need to solve this equation. Instincts, what should I do? Anybody? What would be my first step to try to solve this equation? You factor the numerator. I still got this denominator that's bugging me out. Yeah, why don't we multiply both sides by x minus 1? That way, everything's on the same level. How do I solve this? You will see lots of these throughout this year, throughout this course. If you see an x squared and an x in an equation, get everything on one side, set it equal to 0, factor to solve. Okay? I'll say it now. If you didn't think of that right away, you're going to think of that from now on. If you see x squareds and x's in an equation and you're trying to solve, move everything onto one side. Algebraically, subtract 6x from both sides, add 6 to both sides, factor to solve. Now I got two solutions. However, this one was the one that was guaranteed by the intermediate value theorem because 3 is between 2.5 and 4. Given the table of values of a continuous function, give one value b so that the function must have 2 roots. Is there a number to guarantee only 1 root? Okay. This is very, very important introduction to tables in this class. What you guys need to know is that points coming from tables don't tell you as much as you think. Okay? It's very, very important to know that all you know is what's going on here, here, and here, and whatever you decide B to be. A lot of people think, oh, if I put B down here, then the function is probably going to connect smoothly like that. You don't know that. Because could I connect these points, if it's a continuous function, this way? Does that still satisfy the table? This is very important because you will see lots of tables and lots of quizzes and tests. And if you think things go smoothly, you're not thinking about all the possibilities out there. Okay? Now, where does this green dot have to be to guarantee that there's at least 2 roots? Is it up here, here, down here? But first of all, what's a root? Yes, a root is that's important to know. If you don't know that, make sure you know that now. Okay? When we intercept the x-axis, it's when y equals 0. Okay. Where does that green dot have to be? To guarantee that I cross through the x-axis twice, at least twice. Below. Very important. Okay? So, give one value of b so that we must have 2 roots, something negative. Is there a number that we guarantee to have 1 root? Most of you will think 0. Because you're like, oh, look. 1 root. Is it guaranteed that we only have 1 root? No. Back to what I said originally. You don't know that you connect things in a smooth way. This has 1, 2, 3, 4, 5, 6, 7, 8 roots. Okay? Can I guarantee I have 1 root? No. Can I ensure that I have at least 1 root? Yes. So just be careful with the wording. So there, number 2, make sure you have only, for a possibility of only having one root, yes. If this was 0, it's possible that you only have one root. All right, it's a big lesson.